Good morning, everyone. Welcome to today's class. So in this class, we will continue with the cross-validation. Recall that we introduced cross-validation. Basically, our motivation here is to select a good K value, right? So for the K model, since we have to specify what is this K, it's better that we can know, like, okay, after we know which is the best value of the K, then we start to run the KNN for the testing data. So basically, until now, like, when you are running the cross-validation, that means you can validate all of the K values in your training data, right? So that's why here the input of the default cross-validation actually has, like, of course, the list of candidate K. You need to select one K from this list, and then a training data set. This training data set is used for this validation. Like, you can split it into defaults, and then just in turn to select any fault to be the validation set, and then train on the remaining like D-1 faults. Then you can testing in the validation set and then record the error. So this would be the steps of the default cross-validation, which we already illustrated in last class. So recall that it's a nested loops, right? It has like D iterations because each of the fault you can select it to be the validation set. But inside each iteration, it has like Q rounds. Here the Q rounds correspond to the number of possible candidate K values. For each of the K value, you need to have one round and then record the error until after you finish all the nested iterations rounds, and then you can find average error of any K value. So which is like this. So this is a visualization for any single K value. So for example, here you just suppose that you let K to be Ki, and then for these iterations, here we let D to be 10. So that's why here we actually split the training set into 10 faults, and then each iteration we just select one fault to be the testing fault or the validation fault. The remaining would be the training faults, and for the single Ki value, we can record an error, and after the 10 iterations, the average error just computed in this way. For each K value, for each single Ki value, we need to like run this, and so overall at the end, here the question actually we answered in last class. Actually, overall, we will have like Q times D errors in total, right? Because we have Q times D nested rounds, nested steps, and each step we have to compute an error. So in total, we have D times Q errors, but at the end, we only need Q average errors because we have Q K values. So for K1 to KQ, we compute their average errors, compare them, and select the K value with the minimum errors. And because we believe that according to our validation results, this K value actually corresponding to the best performance. And we believe it should be a best K value from this candidate list. So until now, any questions so far regarding the default cross-validation, except the error, because later on we will like immediately follow with how to measure the error. So except, yes, please?
To compute the error, you need to have a true value. So
yeah.
What is the true value that you are computing?
The true value actually we already have because this is a training set. The training set is a labeled training set. So actually for each data sample in the training set, we already have their labels. So after we split it into these defaults, like for example, we select this fault to be testing faults to work as if it's a testing fault, but actually we still have all of their labels. They are stored in the training set. So basically when we measure the error, we compare the prediction results with ground truth labels because actually we have. Thank you for your question. Very good. That's the concept of the validation set. Validation set is that you want to select a small portion of your training set. Like during the training process, you will just treat this small set, this validation set, as if it is a testing set. but actually it's not a true testing because you know of its labels. The main purpose is that you want to validate your training performance on this validation set to say, okay, even though until this moment you haven't seen your true testing set, but at least you can know what will be the generalization performance of your model to some new set. Because for the validation set, after split it, you train in the remaining training folds, right? Remaining training sets, and then basically when you are validation in this validation sets, the model sees some new data. But for this new data, actually you know of its labels because it's originally from your big training sets. So this is called the validation. Yeah, very good question. Any other question regarding the default cross-validation? Great, if no question, then we will go into this question. How to evaluate the model. I know that in machine learning, usually when we're saying evaluate the model, that means we measure the error. How to measure the error for any of course, that's the supervised learning model. So let's see the model evaluation part. So for model evaluation, actually we have to separate into two tasks. Classification and regression, because usually classification tasks and regression tasks have different error measurements. So first, let's see the classification problems. So model evaluation for classification problems, the foundation is that we always need a so-called confusion matrix. So later on, I will tell you what is this confusion matrix. After we have confusion matrix, we have several evaluation metrics based on confusion matrix. That's precision, recall, F1 score, and MCC score. So first, let's start with the binary classification case confusion matrix. So now, just simply assume that we only have two classes. That's the binary classification, right? Then for any two classes, we just regard them as positive class P and negative class N. Then after you do a prediction, possibly you will have some correct predictions and some wrong predictions. Actually, you can all summarize them into this 2x2 matrix. 2x2 matrix, so here it's it only has 4 entries. These 4 entries, in each entry, it counts the number of testing data. So here, suppose we use these columns to represent the predicted class. The first column represents that the testing data sample that have been predicted as positive. And the second column represents the testing data sample that has been predicted as negative. Because for any of the testing data, after you use your model to predict it, it can be positive or negative, right? Only these two possible classes. There's a binary classification. And note that if we want to evaluate the model, actually we have to compare the prediction with the true labels. So here, the rows represent the actual class or the true labels. And the true labels, of course, it can also be positive or negative. So here, the first row represents all the data samples, the testing data samples that have positive as actual class. And the second row are all the testing data samples that have negative as their actual class. So for all the possible prediction results, actually we can just separate them into these 4 entries. These 4 entries, we give them some name, some terminology to refer to the 4 cases. That's true positive, true negative, false positive, and false negative. They lie in these 4 entries. So let's check what are their meanings. True positive, this concept actually it lies in this entry. True positive, it refers to the number of predictions where the classifier correctly predicts the positive class as positive. Right? If you look at this entry, that means actual class is positive. In the meantime, the predicted class is positive. So that's basically the model can correctly predict it, correctly predict the positive as positive. Then similarly, we have true negative. True negative lies in this entry. True negative means that, okay, now the classifier correctly predicts the negative class as negative, because for all of like this entry, basically it means that the actual class is negative, the predicted class is negative. And note that true positive and true negative, that's this main diagonal. The two numbers, if you add them up, basically that's the total number of correct predictions, right? That's either correctly predict as positive or correctly predict as negative. So this main diagonal all represent the correct predictions. Then as you can see, for this diagonal, there are some wrong predictions. It's very common, right? When we do the testing, it's very common that the model just predicts as some wrong class. So for the false positive here, this entry, it refers to the number of predictions where the classifier incorrectly predicts the negative class as positive. Because for this entry, actually the actual class is negative. This one, right? The second row. But the model made some mistakes. The model predicts the data samples here as positive. So it's some false prediction, some wrong prediction. So it's called false positives. It's supposed not to be positive, but somehow the prediction is positive. Correspondingly, we have a concept, false negative, that lies in that entry. False negative then refers to the number of predictions where the classifier incorrectly predicts the positive class as negative. So this entry, we know actual class is positive here. But somehow, the prediction is wrong. The model made mistakes, so the model predicts them as negative, so we call them false negatives. So for this diagonal, they represent all the wrong predictions. And note that all these four entries in a confusion matrix, they correspond to the number of corresponding data samples. Like actually, like this TP, Tn, Fp, Fn, there are some numbers. Like it counts all the numbers. Because after prediction, after you compare your prediction with the true labels, you can count all the numbers here. So this is the concept we call confusion matrix. A confusion matrix basically just record all these four possible cases for binary classification. Then you may ask that, do we have to arrange the row and column in this way? Not necessarily. Actually, if you like, of course, you can use the row to represent the predicted class, use the column to represent the actual class. But note that in this case, your confusion matrix is a transpose of this one, right? After you like reverse the actual class with predicted class, basically the false negative and the false positive should also be reversed. It doesn't matter as long as your definition is consistent with all of these concepts. All right, so after we have a confusion matrix, we can have the simplest evaluation metric and the simplest arrow. What is arrow? Arrow is all of the wrong predictions proportion. So basically, arrow, we know in this diagonal, there are some wrong predictions, right? So that's Fp plus Fn, then divided by the total number of testing data. That's just you add all of these four entries up. This is the arrow. And arrow, we see that is simply just 1 minus accuracy. Now what is accuracy? Of course, accuracy is the proportion of the correct predictions. We know this main diagonal contains all the correct predictions. So accuracy is like Tp plus Tn, all of the true positive and true negative correct prediction divided by the total number of testing data, which is 1 minus arrow. So this is only one special case. First, we see that it's binary classification. We only have two classes. And then we simply use accuracy. Accuracy, of course, the most simple way to do the evaluation, right? Basically, you just count how many data samples are correctly predicted, and then correspondingly, the arrow will just be 1 minus accuracy. You count like how much fraction that the testing data are wrongly predicted. All right, so until now, any question regarding the confusion matrix for binary classification? Great. So now we have a confusion matrix, and we already know how to calculate accuracy according to confusion matrix. Actually, for classification problems, we have many other more commonly used evaluation metrics other than accuracy. They are called precision and recall. Let's see what is precision. Precision, it tells us what fraction of predicts as positive class were actually positive. And the formula would be like this. The precision is true positive divided by true positive plus false positive. So if you look at the confusion matrix, it should be this entry, the true positive entry, divided by the first column. This is the precision. Then another metric is called recall. Recall tells us what fraction of positive samples were actually predicted as positive by the classifier, and then the formula is true positive divided by true positive plus false negative. If you look at the confusion matrix, is the true positive divided by the first row. So these are two new evaluation metrics, precision and recall. So just from the mathematical formula, you may find that they are very similar, right? So basically, we try to measure the fraction of true positive among some sets. Then what are the differences between like these two? They look very similar, so we can refer to this one. So actually, we can use this. I find this visualization is very good. So I directly download it from Wikipedia. We can consider all the binary classification as the visualization like this. So like all these data points are here. Like they are just maybe just arranged in some space, in some sets. And then the left part is called relevant elements. Relevant elements mean that their true labels, their actual classes are positive. So they are in the left side. Then the right side are unrelevant elements. So the right side corresponds to the right half square, corresponds to all the data samples who have the negative actual class, like their labels are negative. And what is this circle? This circle retrieved elements. Circle means all the data samples that have been predicted as positive. So that's retrieved elements. So you can just imagine that now the model tries to retrieve the positive samples from the testing data, and somehow all the data points inside the circle are retrieved elements predicted as positive. Now all the data points outside the circle are predicted as negative. In this case, actually, you can try to think about what are the relation between this visualization with our confusion matrix. And we can find that now the four concepts are also very clearly visualized in this figure. So let's say inside the circle, the left half, like this half circle is called true positive, right? This half circle, actually, their predictions are positive. And in the meantime, their actual label are positive. So actually, this half circle, left half circle is true positive. And then this right half circle are false positive because their actual label are negative. They are in the right half. But somehow they are also retrieved. They are also predicted as positive. So actually, this right half circle is false positive. Then in the left half, this left half square, outside of the circle are false negative because they actually are positive classes. Like they have the actual class as positive, but they haven't been retrieved by the model. So they are predicted as negative. So they are the false negatives. And then the last part, the right half square, but outside this circle is true negative. Like all of these data points, they have negative actual class. In the meantime, their prediction is negative. So we can just try to visualize the previous confusion matrix and these four concepts in such a figure. All right, then let's examine what are the formulas of precision and recall represent. We know that precision is true positive divided by true positive plus false positive. So if we try to look up at this figure, precision is this left half circle divided by the whole circle. The whole circle are all the number of data points that have been predicted as positive. So that's true positive plus false positive. This is the precision. And in this way, we can see the actual precision tells us like how much we can trust the model when it predicts an individual sample as positive, right? This circle represents that, okay, the model predicts all the data samples inside the circle as positive. And if we try to measure this proportion, basically it's just we want to know like how much we can trust this model when we only look at the positive class. Like when it predicts as positive, like whether we can trust it that actually it's positive. So we use precision to measure this metric. Then what is recall? Recall is true positive divided by true positive plus false negative. If we look at these figures, again, the numerator are always this true positive, this left half circle, but in the recall, the denominator are the left half square in this way. So that means the denominator is a number of data points that who have positive actual class labels. Like their true labels are positive, but that's TP plus Fn, true positives, true positive divided by the like actual positive samples. And then what does this recall represent? In this way, we can say recall measures the ability of the model to find all the positive samples in the data set. Like this denominator, this left half square actually are all the positive samples in the data set. And if we want to get the proportion of the true positive among this one, so basically we want to know what is the model's like ability to find all the positive samples. So this would be the different meanings of precision and recall, even though they look very similar, but actually they are inherently different. They measure the model's different abilities, different performances. And note that we need these two evaluation metrics because actually these two evaluation metrics, they are not so correlated sometimes because the model may have very high precision while in the meantime very low recall, or sometimes or very high recall while low precision. But here is a very extreme example. Imagine that we simply classify all the data to positive. Now what will be the recall? Yes, 1, correct, 1. If the model just simply, does not do any like learning, but just simply classify all the data to positive, actually the recall will be 1, the maximum number, right? Recall to 1. You just imagine that now this circle is basically expanded to the whole data set, like just classify all of them to be positive. Recall, of course, is 1. But in the meantime, what about the precision? The precision possibly be very low, right? Because you will make lots of mistakes if you simply classify them into the positive. But that means precision and recall usually like they are not like so correlated with each other. Usually like one is high, another is low, or one is low, another is high. And then is there a better way that try to combine the two evaluation metrics so that possibly we can have a more reasonable, so that we can in the meantime measure these two abilities of a model? Yes, we have such a way to combine precision and recall to try to find a balance of the model performance. That's called F1 score. So F1 score tries to combine the two evaluation metrics into some single measure, and mathematically is the harmonic mean of the precision and recall. So F1 score is 2 times precision times recall divided by precision plus recall. So this is the harmonic mean. If we just replace all the formulas using these four concepts, this TP, FP, Fn, because we know what is precision and recall, right? The mathematical formula are here. Just substitute everything here, then we can get F1 score. Takes this formula. It should be 2 times true positive divided by 2 times true positive plus false positive plus false negative. So this is the F1 score. And in a perfect world, of course, we want a model that has a precision of 1 and a recall of 1. So we want to have like some 100% correct prediction. Actually, if precision and recall are 1, then F1 score is also 1. That is 100% accuracy. But which is often not be the case for a machine learning model. Usually for a machine learning model, after you train it, you do testing in some new data set, usually you cannot have like 100% accuracy. There must be some mistakes. And usually we just use F1 score to try to find a balanced evaluation metric. So any questions so far regarding precision, recall, and F1 score? Great. Now, actually we already learned 4 evaluation metrics, right? Accuracy, precision, recall, F1 score. All of them actually are very commonly used evaluation metrics for classification problems. Here is another one, which is called MCC score, the Matthews correlation coefficient formula. So this MCC score also is just some single value and is a best single value classification metric, which helps to summarize the confusion matrix or some error matrix. And for this formula is somehow like much more complicated. So MCC takes this one. So after you have a confusion matrix, MCC is Tn times Cp minus Fn times Fp, and then divided by the square root of these 4 things. Actually, by the mathematical formula, it seems like somehow complicated, but if you look at the confusion matrix, it's somehow like more easier to understand. So, for example, maybe I just draw a confusion matrix. This is the actual class. This is the prediction. So suppose like this is our confusion matrix, then what is this MCC? TP times Tn. Actually, it's this diagonal you multiply in these 2 elements, right? So so maybe like this is the multiplication of the first diagonal minus, actually it's Fn times Fp. That's this diagonal, right? So you minus this multiplication of just we call it second diagonal. Then what is the denominator? Even though the denominator seems complicated, like it's the square root of these 4 things together, but if you look at the confusion matrix, basically it's the square root of the sum of first row times the sum of second row, then times the sum of first column times the sum of second column. So it will be like easier to understand what is this MCC trying to measure. MCC tries to measure like get the diagonal elements, do the multiplication, and then divide it by the square root of the multiplication of the sum of each of the row and each of the column. This is MCC. So know that if the prediction returns very good rates for all of the 4 of these entities, like these 4, then it is said to be a reliable measure producing high scores. And To show the most correlation coefficients, actually MCC has a value range between +1 to -1. If MCC has a value of +1, then we say it's the best performance. That means it's the best agreement between the predicted and actual values. This is +1. Of course, MCC when it's +1, it's very good. But what if MCC is 0? MCC 0 means that there is no agreement. So basically meaning that the prediction is random according to the actuals. So there is no correlation between prediction and the actual class. Then anyone knows what if MCC equals to -1? Now then -1 and 0 are different meanings for MCC scores.
Every prediction is wrong.
Yes, every prediction is wrong. Very good.
I wonder if the third term of the denominator has a type like Tn plus Fp. Is it
Tn plus Fp.
Should it be Tn plus Fn?
It doesn't matter because we have these two terms here. Tn, we have one term Tn plus Fp and Tn plus
Tp plus Fp.
Tp plus Fp is here. Yes. So yeah, it may not be exactly this order, but anyway, we are just divided by the sum of each of row, each of column. Right. Very good. Yes, very good. Excellent. Actually, you get what a MCC is -1. When MCC equals to -1, basically all the predictions are wrong. So that means they are in totally disagreement between the prediction and the actual values. So actually, we will see that MCC is +1 is very good results. And if MCC is -1, somehow it's also good for us because we simply reverse the prediction, right? You simply reverse the prediction, then you can get everything correct. The worst case actually is MCC equal to 0 because MCC equal to 0, there's no agreement. That's basically some random prediction. So this is the meaning of MCC score, right? Very good. So any question regarding this MCC score? All right, then MCC, another evaluation metric. Okay, so here is an example of MCC. If we have the confusion matrix with these 4 entries, then after we substitute all of these values in the formula, we can calculate MCC is 0.14. In this case, if we have something like that, then 0.14 means that the classifier is very close to a random guess classifier. And hence, it seems that MCC actually helps us to identify the ineffectiveness of the classifier in classifying especially the negative class samples. Because in this example, actually, as you can see, the true positive is very high. In the meantime, the true negative is very small. Basically, if you infer from this data set, you can see it's originally an unbalanced data set. There must be many positive, right, data samples. That's how we can have so many true positives. This is the application of MCC score. So all of the above, actually, they are just for binary classification. Binary classification things are easy. We only have 2 possible classes. Any of the 2 possible classes, we just treat them as positive and negative. But in reality, when we're trying to deal with some practical problem, usually we deal with the multi-class classification. So there are several classes. The number of classes are larger than or equal to 3. In this case, we cannot simply use some 2x2 matrix, right? Because we have so many classes. In this case, we have to do some higher dimension. This dimension is not dimension of array, the dimension of matrix. Higher dimension matrix to represent the confusion matrix. So just consider we have 3 classes. If you want to extend it to 4 classes, 5 classes, or multi-classes, basically that's a direct generalization. So 3 classes are already efficient to illustrate the confusion matrix here. So suppose we have 3 classes. We are doing some fruit classification. So 3 classes: apple, orange, mango. In this case, we have to use a 3x3 confusion matrix to represent all the prediction cases. Actually, if you refer to this one, you may find that we reverse the true class and the predicted class, but it doesn't matter at all. As long as your concepts are consistent with your dimension arrangement, that would be fine. So here is another example. We show you that, okay, what if now the column is true class, the row is predicted class. And again, of course, we can just summarize, we can just put the number in each entry to represent the cases, right? So for example, this entry is 7, means that there are 7 data points which have apple as their true class, and they are predicted as apple. So this is this entry, like apple, apple. And what is this entry? This entry means that, okay, these 8 data points, their true class is orange. They are in the second column, orange, but their prediction is apple. They're in the first row. So for each of the entry, we just put the corresponding number. And for such 3 class classification, of course, in total, we only have 9 cases. Right? If we compare their true class with their prediction, we only have these 9 classes, these 9 cases. So we just simply summarize the number of the corresponding cases in a confusion matrix. And now this confusion matrix records these meanings, but we still need to find what is true positive, true negative, false positive, and false negative. But since now there are 3 classes, we cannot use one set of these 4 concepts to summarize the prediction results. For each individual class, we need to find this TP, TN, FP, and FN. So let's use apple as an example. So if you want to find orange and mango, basically you just follow the same way. For apple, what it means, true positive. True positive means that now for this class apple, both their true class and their predicted classes must be apple. In this case, we find that the true positive of apple is simply this entry, 7, right? This entry represents both their true class and their predicted class are apple. And then what is true negative? True negative means that, okay, both the actual and the predicted values, they are not apple. And we find that in such confusion matrix, there are 4 entries corresponding to that case. These 4. Or we say that this submatrix. So we have such a 2x2 submatrix. Because in this submatrix, these 2 entries, the data sample, their true class is not apple, and their predicted class is not apple. So they are all the true negatives for apple, even though actually we know in this sub-entry there are wrong predictions. Like these 2 entries are wrong predictions, but it doesn't matter. If we only care about the class apple, it doesn't matter. For class apple, anyway, they are correctly predicted as not apple. So for the true negative for apple, still we count this submatrix. Okay, these 4 entries we get, okay, now the true negative should be 8, just simply the sum of this submatrix. Alright, then what is false positive? False positive means that, okay, the predictive value, the predicted class is apple, but it's a wrong prediction, its actual class should be non-apple. In this case, we have 2 entries. 2 entries are here, these 2. Right? Basically, the first row are all the data samples that have been predicted as apple, the first row. But now we only calculate the false positive. So we only need to care about these 2 entries. Some wrong predictions, wrongly predicted as apple. So the false positive would be 8 plus 9, 17. And last, false negative. False negative basically means now the predictive value is non-apple, but the actual class is apple. So these 2 entries. Because the first column actually represents all the actual labels are apple, and we only want some false or some wrong predictions here. So the first row's wrong prediction are these 2 entries. their actual class is apple, but their prediction is not apple, so it should be these two entries, 1 plus 3, which is 4. So by following this way, actually we can just get the 4 concepts. This is only for apple. So if we want to get like the complete information, we also need to find this TP, TN, FP, and FN for orange and for mango. Like the multi-class classification, you need to find all of these concepts, these 4 concepts for each of the individual class. But if you already have the confusion matrix, this will be easy done, straightforward done. If you already understand these concepts very well, basically you can see that the true positive should be the entry in the main diagonal correspondingly. Like for orange, this is the true positive. For mango, this is the true positive. You just find the corresponding entry in the main diagonal. That would be fun. Then the false negative. False negative basically is you find some submatrix which is in diagonal with your corresponding entry. Like if you want to find true negative of mango, then that's this submatrix. But of course, if you want to find the false negative for orange, you somehow need to imagine that. And actually for this case, the false negative for orange, like this entry, and this entry, and this entry, right? You just find the corresponding submatrix, which is diagonal to your true positive entry. All right, then what is false positive? False positive, if you arrange the results like this, that means if you use the row represent prediction, the column represent the true class, and possibly then basically now the false positive should be the corresponding row except the true positive. And then the false negative should be the corresponding column except the true positive. So of course that's if you arrange in this way. So you just need to refer to this confusion matrix, look up each of the entry, and then find all these TP, TN, FP, and FN for each individual class. And we always need these 4 values because like we know all of the evaluation metrics actually rely on these values. Now we can calculate the precision for apple. Precision we know is true positive divided by true positive plus false positive. And then for the apple, we already get all of these values. So apple's precision is 0.29. And recall true positive divided by true positive plus false negative. So apple's recall is 0.64. And as you can see, it's indeed that precision and recall, they are not consistent with each other. Right? In this case, the precision of apple is very low, but the recall of apple is relatively higher. And we can also get the F1 score. F1 score is like computed in this formula, and after that we get a 0.4. But all of these evaluation metrics, precision, recall, F1 score, are only computed so far for apple, for one class. It's a multi-class classification task. Of course, we cannot only focus on any single class. We have to combine all of these classes and to get an overall evaluation matrix to measure the model's performance. So that is, we need to also consider orange and mango. So simply, we just calculate the measures for all other classes. Like after you get all of these 4 values, you can compute precision, recall, and F1 score for orange and mango. And then we can just summarize all of the evaluation metrics of each single class in such a table. But still, we have non-values here. Usually, we don't need like non-values to evaluate one model score, right? We cannot see anything from these non-values. Like some are high, some are low. Like maybe the model performs better in some class, performs worse in some class, but how to combine them? Like how to combine the F1 score of each class to have a single measure, have an overall measure for this model. We have 3 different F1 scores. If we consider multi-class classification, they're called micro F1, macro F1, and weighted F1. First, micro F1. So micro F1 is calculated by considering the total true positive, total false positive, and total false negative. It does not consider each class individually. It tries to calculate the matrix globally. And for our example, the total true positive is you simply add the true positives of the 3 classes together. Now the total true positive is 10, and total false positive is you add the 3 false positives of the 3 classes together, and we get 26. Similarly, we can get like total false negative as 26. And after that, we do the global evaluation. Like the precision, still we use total true positive divided by total true positives plus total false positive, which is 0.28. And recall, according to that formula, we calculate 0.28. Micro F1, using this formula, get a 0.28. So now you can see a strange thing that precision, recall, micro F1 all get the same value. Is it coincidence or is actually will always like this? It will always be like this. So if we calculate in the matrix globally, all of the measures become equal. Not only the 3 become equal, actually if you find accuracy, you will find that precision equal to recall equal to micro F1 equal to accuracy. If we consider the total true positive, total false positive, and total false negative of the model. Actually, this is not hard to prove. By referring to the formulas of like these 4 metrics, I think you can prove that. Actually, you can directly prove that why, if we consider it globally, these 4 metrics, they simply become the same one. So that means if you want to calculate the micro F1 for multi-class classification, basically you only need to get the accuracy. Accuracy is the easiest thing to calculate, right? So you just get the accuracy, and all of the other metrics are just the accuracy. So that's why actually in the academic community, usually the micro F1 is somehow useless. Even though in concept it has of course it has the evaluation meanings, but in numeric it's always equal to accuracy. So simply you can just calculate accuracy. Then the second one is called macro F1. Macro F1, now it calculates the matrix for each class individually and then take the unweighted mean of the measures. According to the previous data in the table, like here we already calculated the matrix for each of the single class. Now this macro F1 gets the average of their F1 scores of these 3 individual classes. So after that, the macro F1 will be average of these 3, so which is simply 0.24. So macro F1 usually is more commonly used than previous micro F1 because now actually it considers each of the single classes. But still, sometimes we find that the macro F1 is not enough because possibly in our testing data, the different individual classes, they are not so balanced. Possibly like some classes, they have more data points. Some classes, they have less data points. If we just simply take some unweighted average here, it may not very precisely reflect how the model performs. In this case, we use weighted F1. Weighted F1, now it takes the weighted mean of the measures. And what should be the weight? The weights for each class are the total number of samples of that class. Since in this case we have 11 apples, 12 oranges, and 13 mangoes, we directly use these 3 numbers as weights. These 3 numbers, actually you can look up the confusion matrix. How many apples do we have? Basically in the first column, right? And how many oranges do we have? The second column. You can just get all the numbers by looking at this confusion matrix and then get the weights for each of the class. Then the weighted F1 just be like this. You take the weighted average. And by the way, this 0.24 is the same with this 0.24. This is a coincidence. It's not necessarily like this. All right, so we have like these different ways to calculate this F1 score. So let's sum up a little bit so that you can know like how much we have gone so far. So multi-class classification, first you need to summarize all of your prediction cases in a confusion matrix according to how many classes you have. Like if you have 4 classes, then you need to have like 4 by 4 confusion matrix. After that, for each single class, you need to compute their TP, TL, FP, and FN, and you compute their precision record and F1 score for single class. And after that, you have these 3 possible different ways to combine their F1 scores to get an overall evaluation of the model. All right, so until now, any questions so far regarding this multi-class classification? Okay. Yeah, so basically that's for the classification cases. For classification problems, we have like this evaluation matrix. And for binary classification, you already know. And for multi-class classification, just try to extend them to this multi-class case. By the way, we omitted the MCC because MCC score for multi-class classification is much more complicated. The formula is very, very long if you look up at some mathematics books. So here we simply omit that MCC for multi-class classification. And yeah, let's recall why we would introduce all of this. Basically that we want to measure the error in default cross-validation. And the error, measure error, which is equivalent to evaluation of the model performance. And so actually we have learned many evaluation metrics, right? Then you can just choose the most appropriate one. Let error be 1 minus some evaluation metric. Like if you want to choose accuracy, then the error would just be 1 minus accuracy. If you want to choose F1 score, then error would be 1 minus F1 score. So this would be the error measurement during the default cross-validation step. And this is for classification problems, but we have another type of problems which is called regression in supervised learning, right? Now, for the regression problems, again, there are many ways to measure, and there are 3 most commonly used ones. Mean absolute error, MAE, so which is from like the sum of the absolute value of the difference between actual labels with predicted label. So AI is the actual label, PI is the predicted label. And you get the difference of, and then absolute value, sum them up, divided by M. M is the number of testing data points you have, because you want to get some overall measurement for your testing data set, right? So this is the M. And since it's for regression, so know that all of these AI and PI, there are some values in some continuous range. It's a regression problem. Another metric is called the mean square error, MSE. And now it's the sum of square of the error, like AI minus PI square, and then sum them up, divided by M. And last one is called mean absolute percentage error. This is similar with MAE, but we get the percentage. So this difference, we divided it by AI and then get the absolute value. But know that if we use this mean absolute percentage error, we need to make sure that the continuous value range does not include 0. So otherwise, like if AI is 0, of course, we will encounter the problem, the 0 denominator problem. So this would be the 3 error measurements for regression problems. All right, so for regression problem, usually things are much easier. But for the classification, somehow everything is relying on the confusion matrix. And you may ask one question, I think you care it very much, like, do you have to memorize all of these formulas? No need. In exams, if we want you to calculate any of the error measurements or previously any of these evaluation metric, we will provide the formula, but you need to know what these four values mean. Like you need to know what is true positive, true negative, false positive, false negative for both binary and multi-class classification. Basically, when given a confusion matrix, you have to know how to get these values. And after that, all of the formulas like precision recall, F1, MCC, we will provide to you. So no need to memorize these formulas. You only need to figure out what the concepts represents. All right, so any questions so far regarding the, yes, please?
For the MAP, to prevent the denominator becomes zero, do we need to use the Laplace smoothing?
Laplace smoothing, no need, because after if you add some smoothing, possibly the meaning of the labels will change, because now it's regression problem. Regression, like the value have some exact meaning, like the value is usually in a continuous range. For example, now the labels, for example, may represent the height, the weight, something like that. If you add some terms, then it may just change the meaning.
Also, the smoothing is not suitable in these.
Right, smoothing not suitable for the regression problems.
Okay,
Yes,
thank you.
very good question. Thank you. Any other question? Great. If no other question, I think let's take a 3 minutes short break. After that, we will continue with the remaining contents of KN.
If there's any hidden case for the lab or the
Yes, there will.
for both lab.
Yeah, for both labs. So after that, we will use the hidden test cases.
Hidden case. So it's C++.是直接 logic。
算是经验咯。
When you see the question, you can provide the formula. All right. Yes. Let's come back to the class. So not at all of these things, because we want to answer this question: how to evaluate the model, how to measure the error. So after incorporating this step, now you already know the complete information of how to conduct the default cross-validation. That is, each step we record the error. Record the error is that. Recall that now you need to classify your data in your validation set. Basically, now your validation set is your testing set. Classify the data in your validation set, and then after you get the prediction results, you compare the prediction results with all of their true labels, and then compute their arrows, record the arrow, and then at last you can select the value of k with the lowest average arrow. And so now this default cross-validation is complete because you already know each of the steps and how to do each of the steps. Great, then next would be some analysis on the KNN, some overall analysis. Pros and cons. The pros, very easy to understand, right? We already know like the saying, all of the steps are quite straightforward, and it made no assumptions about the data. And know that actual KNN can be applied to both classification and regression. In our class, we only illustrated the examples of classification, like classify the customer's t-shirt size into M or L classification, but it can also be used to do regression. For KNN regression, the resulting value, previously classification, we have to do majority vote. Majority vote use it as classification, right? Now the regression, the resulting value can be calculated by taking the average of the output value for the top k nearest neighbors. So imagine that, for example, after you made some sorting of the distances. Suppose this is your testing data, and then this is, you have like take, okay. Suppose you have taken like 5 nearest neighbors. Now I always circle doesn't mean that they belong to the same class because it's a regression problem. So suppose we deal with regression. So all of them are just data points. And then for the data points, they have some labels. And their labels are some values in a continuous range, right, in regression. Then the prediction for this testing data, you just take the average of these 5 nearest neighbors' label values, and then use the average to assign its label, because the labels are now just in some continuous range. All right, so this is how you can apply KNN to the regression problems. And it works easily on multi-class problems. Of course, for classification, you just do the majority votes. But still, there are some remarkable disadvantages of KNN. I believe you may already find that if you have done Lab 3. It's very memory intensive and computationally expensive. If you want to implement your KNN from scratch by using NumPy, possibly you encounter this problem. You will find exceeding the Google Colab's memory, and also it takes you like so long time to run the KNN. Possibly that's not your problem. I believe that actually you implement it already very efficiently. You haven't used any for loops. You use everything like using NumPy functions, vectorization, but still you encounter this problem. Yeah, that's because KNN itself is very memory intensive and very computationally expensive. All computations, if you consider like during the testing, it has to compute the pairwise distances between 2 data sets, between training and testing data set. And the computation of these pairwise distances actually are very consuming. And all of the distance values have to be stored in some array, in some 2D arrays, and the whole process actually consumes a lot. This is the disadvantage of KNN. And actually, it's very sensitive to scale of data. Like you're using different data scales, and then performances will be like very different. And KNN struggles with high number of attributes. That's when the data dimension is too high. KNN struggles a lot, especially if you consider the dimension is too high when you're computing the pairwise distances. Yeah, it will like, actually it takes lots of time, lots of memory to do this. And it does not work well with categorical features, since it is difficult to find the distance between dimensions with categorical features. Categorical features mean that the feature itself takes some discrete values. Like in previous our examples, our features are height and weight. Our features are continuous. right? There are some values in a continuous range, and it makes sense to calculate the distance between the continuous feature values. But if it's category features, let's take an example here. Suppose, let's go back to our animal classification. We have a feature color, which is black, white, yellow. And we also have, for example, the animal size. It can be a small one, and medium one, and large one. In this case, they are categorical features, right? They are not some numbers in continuous range. They are categorical features taking these discrete values. Of course, if we want to calculate the distance, we need to first encode them. Suppose that we just use 0 represent black, 1 represent white, 2 represent yellow. Then in this case, we may find that the distance between black and white is shorter than the distance between black and yellow. And the distance between black and white equals the distance between white and yellow, which doesn't make sense at all. If the features, they are already a category, you just use some integer numbers, use some integer index to represent them, to do the encoding, then the distance doesn't make sense at all. So in this case, KN actually doesn't work very well with these categorical features. A distance might be problematic to compute, but recall that actually we introduced one distance function, Hamming distance. Note that if indeed we have to deal with such categorical features, we may consider the Hamming distance, but first we need to do one-hot encoding. One-hot encoding to try to encode all of these integer numbers into some binary bits. And then we compute the Hamming distance between them. So later on, when we're talking about multi-layer perception, we will let you know more about this one-hot encoding. But until now, you only need to categorize that actually the KN has such a disadvantage. Does not work very well on the categorical features. Then how to speed up KNN? It seems like the most significant shortage is that its speed is very slow, its memory is very extensive. Usually, before we do KNN, especially when we're dealing with high-dimensional data, we have to do the dimension reduction first. Only after dimension reduction, the pairwise distance will be easier to calculate. So we can reduce the dimension of training data. There are many possible ways to reduce dimension. One of the most famous one is PCA, the principal component analysis. Actually, yes, please.
Can we use GPU to accelerate the process?
Yes, we can. The GPU, but I think in Google Cloud still the GPU has limited resource usage. Yes, so still it consumes a lot. Yeah. So especially that after, possibly after you run out your GPU limits in Google Cloud, then it will go back to slow again. So, but yes, we can use GPU. Typically, GPU actually, the programs will run faster. But it's the improvement on the hardware instead of on the algorithm itself. Very good. So dimension reduction, most famous one, principal component analysis. Actually, we provided it as the supplementary notes in the K-means clustering. So if you're interested, you can refer to the supplementary notes about PCA. For this course, we do not require you to know the details of PCA, but still you can have a general concept that PCA can be used to reduce the dimension. And we can also try to use some good data structure to store the data, for example, the KD tree. But again, this is it's not directly improve the algorithm. It's try to do some data pre-processing, try to use the good data structures to alleviate the problem. And we can also try to parallelize the distance computations, of course. Actually, in this way, it can be speed up a lot. Usually, if you find any algorithm takes too much time, then parallelization would be a good choice. But still, just in this course, we do not require you to know like how to do this parallelization of these computations. So these are some possible ways that we can use to speed up KNN. And for the KNN applications, since it can be used both in classification and regression, so yeah, very good application like the handwritten character classification, just like this. For each of these handwritten, use KNN model to try to classify it into the digits, like from 0 to 9. And it can also be used to the fast content-based image retrieval, intrusion detection, and also false detection for semiconductor manufacturing processes. These two cases actually KNN are very appropriate to do this thing. Because basically KNN it tries to measure the distance or the similarity between any testing data with the neighbors, right? So that means if there is some intrusion in some product, then it will easily be found out using this KNN, this method. And last, we have a practice problem for you. So you can try to like solve that. So in this case, again, we have two features, age and salary. They are some like continuous features, right? They are in some continuous range. And it's a classification problem. Label purchase can only be yes or no. It's a binary classification. So you can try to solve that and then refer to the appended solution to see whether you can get it correct. All right, so basically that's all the contents about KNN. Any questions so far? Very good. If no question, I think we can end earlier today. And know that next Tuesday is a public holiday, so we won't have any class on next Tuesday. No lab in next Tuesday, and we also cancel next Monday's labs. So next week, no need to attend the labs. Yes, very good. Enjoy your holiday and see you on next Thursday.